Orbital inclination, 20 degrees. Although the evidence presented by Battigan and Brown appears quite compelling, no one is certain if Planet 9 actually exists. Until it is directly observed, its existence cannot be scientifically confirmed. So where might it be at this moment? For now, no one is sure, but studies conducted thus far offer a general idea of its movement in the sky and its brightness. Current scientific efforts are aimed at narrowing the search area. For example, recent simulations by Battigan and Brown have reduced the possible location of Planet 9 to about 600 square degrees. For comparison, the entire celestial sphere covers about 40,000 square degrees. Excluding areas already surveyed by automated systems like Pan-STARRS and WISE, the most likely conclusion is that Planet 9 could be near its aphelion, about $600 away. Statistically, an object orbiting a star spends significantly more time near its aphelion due to its slower speed at that point. Even if Planet 9 exists and is large, it would be extremely faint at its expected distance from the Sun. You might assume that if it were 10 times farther than Uranus and nearly the same size, it would be only 100 times dimmer, since brightness decreases by 1 over the square of the distance. However, sunlight encounters this issue twice from our perspective. The sunlight reaching such a distant object is 100 times dimmer than the sunlight reaching a closer one, but then the reflected light must travel 10 times farther back to Earth. Instead of diminishing by 1/r superscript 2, the light we see decreases by 1/r, making any object that far away exceedingly hard to detect. Very faint objects can be found through dedicated astronomical surveys, but locating an object that doesn't emit its own light like a star and only reflects sunlight is further complicated by this issue of reflected sunlight. For an object twice as distant as another, the light must first travel twice the distance, allowing only 1/4 of the light to reach it, and then return over twice the distance, resulting in just 1/16 of the initial brightness. The 1/r drop-off in brightness is severe. Its magnitude would be around +22, a brightness within the capability of professional telescopes, but unfortunately near the center of the Milky Way. If this rough estimate is correct, finding Planet 9 could be extremely challenging given the dense star fields near the galactic core. In short, the debate over Planet 9's existence continues, with its share of highs and lows. This ongoing discussion, sometimes marked by heated disagreements, was reignited a year ago by a study titled "No Evidence for Orbital Clustering in the Extreme Trans-Neptunian Objects." The authors of the study, led by Kevin Napier from the University of Michigan, argue that there's nothing particularly unusual about the orbits of the 14 TNOs cited by Brown and Battigan. They propose that the clustering of these objects could simply be a statistical anomaly. Their idea is that because these objects are few, small, dim, and extremely difficult to detect except on rare occasions, the apparent grouping in a specific part of the sky could be more about the characteristics of the telescopic surveys used to find them, rather than the presence of a massive attractor. It's possible that their distribution is uniform across the celestial sphere, which would negate the need to suggest a perturbing planet. Naturally, Brown and Battigan disagree with this assessment. Battigan's response reflects their strong position: "I'm still very optimistic about Planet 9. If you see a bunch of bears to the east, you might think there's a bear cave there. But Napier is saying the bears are all around us because we haven't looked everywhere. That's not a logical conclusion. To resolve this matter, more observations are necessary to identify a greater number of trans-Neptunian objects, which would help determine if the clustering that led to the Planet 9 hypothesis is real. Planet 9 will likely keep astronomers busy for years, but new data that could settle the debate may emerge soon. Since the planet is expected to be in the northern celestial hemisphere, the main search is currently being carried out with the Subaru telescope on Mauna Kea, Hawaii, which has both the large aperture needed to see faint objects and a wide field of view to speed up search times. Meanwhile, in Chile, the Vera Rubin Observatory is under construction. This observatory, equipped with the powerful Large Synoptic Survey Telescope, will conduct surveys of the southern hemisphere's night sky, mapping Kuiper belt objects with precision and likely discovering more trans-Neptunian objects. The American astronomer Vera Rubin, for whom the new telescope is named, was a trailblazer in studying galaxy rotation and in defining dark matter, which is the invisible material thought to make up about 85% of the universe. Reflecting on the complexity of her research, she once remarked, "Many mysteries of the universe are still hidden from us. Their discovery awaits the adventurous scientists of the future." Planet 9 is certainly one of those mysteries. It's also a bit of a mystery why, in recent years, astronomers have taken to assigning newly discovered solar system objects names that are nearly impossible to pronounce and even harder to remember. Why do we say this? Well, do you know what the little goblin was officially named? Leleokawanua. In Hawaiian, it means something like fly until the land appears. It's a poetic name, but we do miss the days of Pluto, Eris, and Sedna. Now, along with Leleokawanua, we have names like Oumuamua, Sarajan and Shikumarkan. What do you think? Shouldn't one of the criteria for naming celestial objects be how easy they are to pronounce or remember?